Good evening, and thank you for providing me with the opportunity of talking to you this evening on a somewhat perhaps unconventional topic, and there isn't an obvious relationship to geology perhaps in the title, but hopefully by the end of the evening you'll have some insight into why the consequences of the event that took place in 1944 was very much influenced by geology. I was going to start by reading out something to you concerning the explosion at Fauld, and this was written by a military historian, and I thought he rather summarised the events in a very interesting way. At 11:13 a.m. Greenwich Mean Time, on the morning of the 27th of November, geophysicists in Casablanca noticed a sudden peak register on the recording chart of their seismograph, indicating a significant earth tremor somewhere in the Earth's northern hemisphere. Seconds earlier, Squadron Leader Annes, temporarily in charge of the huge underground bomb store at Fauld near Burton-on-Trent in the middle region of England, watched in horror as the hillside above his underground depot rose bodily before his eyes, broke asunder in a searing fireball, and erupted in a towering pillar of flame and debris a quarter of a mile in diameter. It rose 2,000 feet into the air before opening out into a mushroom cloud of smoke, rock debris, and white-hot unexploded bombs that minutes later rained down on the surrounding villages and farms, bursting in the air as they fell and exploding on impact on the ground. The explosion at the time was the most powerful single explosion the world had ever witnessed, and was the result of the sympathetic detonation of 4,000 tons of high explosive bombs, stored in galleries in a gypsum mine 90 feet below the fields of the Upper Castle Hayes farm. This initiated a catastrophic chain of events resulting in widespread destruction and, sadly, the loss of 70 military and civilian lives, many of them far beyond the immediate boundary of the RAF facility. The crater left by the explosion was once 100 feet deep and covered a quarter of a square mile, but now little reduced some 80 years later, weathering still to a prominent feature on current Ordnance Survey maps, and is clearly visible as a satellite image. So my talk this evening is going to be divided really into three parts. I think it's important that you understand the historical setting and why the Fauld mine was necessary. I think it's particularly interesting in light of the current state of affairs in Europe. The event itself stimulated a number of interesting geophysical studies, particularly on cratering, and the timing was quite interesting with regard to the nuclear testing which was initiated shortly after events at Fauld, and the consequences of that event also has drawn the interest of scientists interested in how the craters on the moon were developed. And lastly, which will be about the last third of the talk, I want to explain why geology had such an impact on the explosion and was really largely responsible for the huge loss of life that resulted. This remained under the 40-year rule an official secret until the 1980s, and so people unfortunately were not able to disclose the consequences of the events other than the people that were working for British Gypsum. So let's go back to 1936, again, something that we're sort of experiencing at the moment. The Air Ministry, which was the Johnny come lately after the Army and the Navy, was going to be taking, or it had realised it would be taking part in a much greater conflict. And it was developing a number of weapons programs. And it realised that it would become vulnerable to attack from the air. And they were looking for somewhere to store the large amounts of ammunition within the UK that were secure. And a number of underground mining operations, particularly the gypsum mines, were shortlisted. The arrangements were that there were, in the RAF decided they were going to have 3 underground depots, and that's what they were looking for. I was fortunate where I was working that most of the correspondence surrounding the Air Ministry's inquiries had been preserved, and I got the original letters from the Air Ministry making their inquiries. One of the key factors at that time was transport. The Air Ministry needed to move large quantities of munitions, and that was only possible by rail at that time. The manufacture of munitions was taking place in Staffordshire at Swinnerton, and the supply chain effectively was from manufacture to the central underground store, and then forward by rail onto the airfields where the ammunition would be loaded into, in this case, aircraft. There were other forms of munitions stored there, but it was primarily associated with what became the RAF. Initially, they were looking for somewhere to store 50,000 tons. They were looking for 20 metres of cover. They didn't understand at that stage what the geotechnical difference was between solid cover, that's rock, and drift. That significance was to come back to bite them big time. It needed to be dry and, as I said before, close to a railway line and remote from centres of population, but more particularly any extractive operations. In selecting the Fauld Mine in Staffordshire, they broke all of those criteria, but needs must. Remind you of the geography. The Fauld is conveniently sited. Let's see if we can get this to. No, the pointer doesn't work. Never mind. In the middle of the country. A gypsum mine, an important gypsum mine. They've been mining gypsum there since medieval times. It was the primary source of alabaster in the UK and most of Europe. Its central geographical location and its rail link, which is in the next slide. These are all the railway lines through the Midlands in, I think this is red, and the Fauld site you can see right in the middle, and we've got an east-west railway line supplying most of the airfields which are situated over in Lincolnshire and East Anglia. The site that was selected was known as the Fauld Mine, which at the time was almost exhausted. It was mainly developed in the 19th century, and it used what was called a random room and pillar system of working. You can see the rather complex picture of what are known as pillars, and the gaps in between are roadways. Most of this was work using hand labour and horses. A room and pillar mine should look like this. This is a modern example. You can see the pillars are left by support in working a seam, and the galleries in between are called rooms. The pillars support the roof, so there's no need generally for any artificial support. And particularly beneath properties, large protection pillars where no extraction would take place would be normally left. That's a rather poor photograph of a typical example of the condition of Peter Fauld's mine. You can see the gallery in the middle with the roof and the pillars situated either side. The layout of arrangements on the surface is shown in this slide, and you can see the railway lines which linked the mine output to a processing mill which was situated on the surface. They made plaster, principally, but they also made plasterboard. There were a number of entrances into the mine, which are shown on the slide here. And take note of the Upper Castle Hayes farm just right at the bottom there, which effectively became the centre point of the underground store. There was a mine adjacent to Peter Fauld's mine called Staton's Mine, and that continued to work through the wartime period, had its own separate entrance and railway structure, and effectively was the development that had taken over following the Peter Fauld's closure. There was a small area to the south, the Peter Fauld's 1940s mine, that was also being developed at the time. And this is what the Fauld's plasterwork looked like. Very nice rural setting, not many people living in the area. Everything you can see there was obviously coal powered from the haze over the top of the factory. This is looking from south to north. The factory was supplied with water from the reservoir, which you'll see at the bottom of the image there, and just to the north, at the top edge of the slide, is the River Dove, which flows in an east-west direction. And another view of the linear nature of the factory and the very wooded, attractive surrounding countryside. When the Air Ministry took it over, they started to reuse the railway system, and they installed an underground network of rail-linked routes to bring munitions to storage underground. In this example here, these are 250-pound GP meaning general purpose bombs. This is how it was stored underground, same sort of bombs, some artificial support required with the girders, but not a lot. You can see the top of the gypsum seam here. Typical working heights would be 2 to 3 meters, so plenty of room to work in. And most of it was fairly dry. You can still visit the site. This is what it looks like today. This is near to the surface where artificial support was necessary because of the fact there was no rock above them, and they were constructed these features to stop the sand which was above running into the workings. So in the 1930s, we got most of our military strategy completely wrong. We were thinking we would be fighting in northern France in trenches. We soon found out that we weren't, and we were stuck in the UK being bombed by the Germans. Fortunately, we won the Battle of Britain, and the German Blitz campaign failed. And the only way that the Allies could hit back at Germany was by bombing, and Fauld Mine was at the centre of the supply of the munitions throughout most of the country in order to allow that to take place. As a consequence, the original capacity at Fauld Mine was increased to 632,000 tonnes of high explosives. In addition, the mine was also used for the repair and maintenance of munitions. When aircraft operate, they often brought back munitions that they hadn't used, and these had to be brought back for removal of fuses and for other maintenance. So this facility also became an RAF maintenance unit, number 21. By the middle of the 1940s, the Americans had come on the scene, and they got nowhere to store bombs either. So there were American personnel who was billeted at Fauld to operate their blockbuster bomb systems. Later on in 1944, the Italians decided that they would change side, and Fauld Mine had a contingent of Italians working there at the same time. So the final storage arrangements were like this. This is a diagram or map showing the sorts of activities that were taking place. So we had incendiary devices and detonators stored at the north end of the mine. The old high explosive store was extended, and a new high explosive store was created with a blast barrier constructed around it with the Upper Castlehays pillar at its centre. Mining operations were still taking place in this area to the south and in the Statons mine to the west. Another example of what the underground situation was with the extension, this was the incendiary and detonator storage area with artificial concrete supports associated with it. This is the maintenance area. The AID is Ammunition Inspection Department, and the ammunition inspection bath is presumably used for obvious purposes, to stop it blowing up. This is a rather posed photograph showing some of the operations that were taking place. I'm sure they actually weren't working like that at the time, and I noticed the officers taking a particularly close attention to what was going on. The trouble is they obviously didn't pay quite enough attention to what was going on. I mentioned about the railway lines. You can see it was quite a complicated set of track work to move these munitions all the way around the mine. As I started my talk just after 11 o'clock on the 27th of 1944, November 1944, between 3,500 tonnes and 4,000 tonnes exploded. Gives you an example of how it compared with Hiroshima, which became the biggest. Hiroshima was 5 times bigger. It produced a 5-hectare crater. They actually don't know how many people were killed. Many bodies were not found for obvious reasons. Sadly, 31 of those people were in the nearby factory. They didn't die as a direct result of the explosion. They died because the dam burst, flooded down the valley, and they were drowned. There were 14 killed in the store, which is quite surprising compared with the number that died on the surface. And to this day, there are 2,000 tonnes of high explosive that are still unaccounted for. Record keeping was so poor within the facility, they actually didn't know how much they got in. It was further exacerbated by the fact that you had no overall control of the site. We had the RAF, the American Army Air Force, and Italian prisoners of war who had decided that they didn't want to go back to Italy. In the circumstances, I couldn't blame them, and they were employed in the mine. So you can see the overall management would probably lead a great deal to be desired. The surrounding area was mainly agricultural, but nevertheless the village of Hanbury, which was the nearest to the centre of the explosion, was very severely affected. The inquiry that took place sometime after the event, whilst most of the evidence had evaporated, unfortunately, it was thought to have been caused by the incorrect maintenance and removal of one of the fuses, a composite exploder from a 1,000-pound bomb. And that should have taken place elsewhere and not in the AG store. I'll go over that fairly quickly. You can see the size of the crater, which is in the centre of the image. The rubble barrier wasn't very effective. Many of the men who were working, in fact nearly all the men who were working extracting gypsum during the wartime there, most of them died because of gassing. The gas was mainly carbon monoxide and the oxides of nitrogen. The most sad incident was a boy had started work that day. It was his first day at work. He was too young to join the armed forces, and sadly that was the last time he went to work. To give you an idea of what it might have looked like, this is a smaller explosion that took place when an ammunition boat exploded in the United States, Mount Hood. So you've got about a 2-kilometre high black cloud. High explosives usually give you very black clouds, and this was a surface air blast, whereas the Fauld one was an underground one. You'll be familiar with the more recent big explosion at Beirut. Similar kind of setting, not about half as much went up at Beirut, 1.5 kilotons of high explosive TNT, again several kilometres up in the air. So you saw that slide earlier on, that's what it started off like, and that's what happened at the end of it. There's virtually nothing left of the factory. You see a couple of guys there looking for casualties. Another similar shot. The factory was totally destroyed. And this is the dam that we saw earlier. The dam wall failed, all the water went down here, and this wall of mud killed anybody who survived as a consequence of the explosion. This is the pub in the middle of Hanbury, and there were animal carcasses distributed throughout the area. Underground, the roof came in places, lots of roof falls. The area with the unexploded ordnance was recommissioned. The site, in fact, operated right up into the 1970s. This is the area where some of the explosions occurred. You can see it's black as a consequence of the soot from the explosion. And that's one of the pillars, what I call an apple core pillar. The vertical lines were the original dimensions, and the heat from the explosion chemically altered the gypsum and eroded that away and that away, which led to a further collapse of the workings. Similar story there, you can see the face has collapsed. And lastly, another feature that they hadn't realised is that the red stuff there is running sand that ran into the workings, which was significant, we'll see in a minute. These are the aerial photographs that were taken at the time. You can see the crater in the centre there, looking something like a lunar feature, and then there are a whole series of other smaller subsidiary craters that were produced as a consequence of the bombs detonating on impact. This is a topographic map, more or less showing the same features. We have, we've got a pointer now. A crater. This is where most people were living, in Hanbury. That was a cock inn where you saw the demolition. We also had a look at Hanbury Fields Farm, and unfortunately the people that lived in Upper Castlehayes Farm were never seen again. Start to analyse now some of the effects of the explosion. There were two zones, an inner zone where we have the main cratering taking place, and then up to some 750 metres, 3/4 of a kilometre away, Hanbury Village received extensive damage. Effectively, this became the zone of the air blast and the ground wave damage. An oblique photograph taken looking due north, and you can see a number of interesting features. This is the crater that was produced, and these are the subsidiary craters that resulted from the exploding munitions when they reached down to the back onto the surface. This was the site of the reservoir, and the factory was just off to this side here. Shortly afterwards, we saw the crater start to change, and the raised rim is much diminished, and the sidewalls start to slump in, which is much the position that it is today. I don't think I'll bore you with the physics of blasts. This is slightly more interesting. Looking at storage of munitions and different sorts of designs of explosions, there are three principal situations. The Fauld design was thought to be like this. In other words, a confined situation whereby if an explosion occurred, nothing would happen at the surface other than it be raised slightly. That's the intermediate position, and that's actually what Fauld ended up like. So that was the design, and it formed a huge crater. So I asked the question, why did they get it wrong? This shows you again, much of the same thing, where you have different types of settings for the location of charges running from near surface all the way around to subsidence craters, where the dot there is the locus of the explosion. Fauld ended up in this position here. I mentioned that the explosion was so large that it attracted the interest of a lot of geophysicists. It was the biggest one anybody had encountered. And this is the heading of a paper by the famous geophysicist Harold Jeffreys, which was the first attempt to analyse the geophysical situation at Fauld. Interest continued, and this is the NASA data that they released in the 1980s. They were looking at the Fauld crater, and this is their basic data from their database that they published, and they called these features astroblemes. And they have the data here of the size of the explosion, and interestingly, they identified that in fact it is not a perfect circle, it is an ellipse, and it has a rim around the edge of it. And they were particularly interested because it was more or less exhibiting the same kind of features as the lunar craters. Don't think we need to go into that, but come on. There we are. That more or less says the same thing, but we have a figure for the ellipticity of 18.5 degrees and the significance of the crest rim and the double walled structures. So we get to some geology now. So this is a bedrock geological map of central England. The dark red is the Permo-Triassic Mercia mudstone group. Fauld Mine sits right in the middle of the Needwood Basin, which is a Triassic evaporating basin, hence the deposition of gypsum and halite. Just to orientate yourself in terms of the stratigraphy, this is the Mercia mudstone. The gypsum seam that was being worked is the Tutbury sulfate bed. There are other sulfates above that which are not economically interesting, and beneath it is the Stafford halite. That's what it looks like underground. That's the, in that case, it's alabastrine gypsum. The Tutbury sulfate bed is 2 to 3 meters thick, quite a decent thickness. This is the geological map of the site. The black line is the position of the mine workings, the modern mine workings. The bomb store is situated here in this area. So mining now is, this is quite an old example, but you're looking here, these marks are kilometre squares. So you can see or get an idea of the scale of underground extraction, which is probably quite a bit bigger than that when I drew this map, which would be in the probably about 10 years ago. The Mercia mudstone is the pinkish red colour, and the outcrop of the seam, this Tutbury seam, is this dotted line here. So all this area is underlain by the Tutbury gypsum seam. What the RAF didn't know was that most of the Mercia mudstone is covered by Anglian glaciogenic deposits. Some of those glaciogenic deposits are sands and gravels, which are in this fluvio-glacial ornament here. Most of this is glacial drift under, and the thickness is up to 30 meters. So dissected plateau, quite old ice deposited these Anglian deposits. Reacquaint yourself with the geography. You can see that the higher ground is in fact formed by the glacial drift resting on top of the lower ground, which is formed by the Mercia mudstone. The glaciogenic deposits are extensively dissected by these deep valleys associated with runoff to the north to the River Dove. The numbers here are the boreholes that British Gypsum had drilled over a number of years, which revealed the thickness of the glaciogenic deposits. This is an example here of one of the craters that I visited now in the wooded area, and you can see the sand and the pebbles associated with the Anglian older drift exposed in this bomb crater, mainly reddish brown sands with flints and quartzite pebbles. I go to a little closer examination of the glaciogenic deposits. You can see that they are very unconsolidated. Underground, most of the gypsum seam is karstified. So underground water probably during the latest ice age has produced a series of caves. And those caves are filled with the glaciogenic deposits. You can see here this is the margin of one of the cavities, and these are bedded sands and silts. Because much of it was sandy, and you'll see here this is a brick wall in the middle of the mine workings, and it says danger, running sand behind this barrier, 1946. Similar feature, this is in the some of the alabaster seam, and you can see here the red glaciogenic deposits in a cavity. So in fact, looking at this cross section here, you can see that the horizontal lines are rock and the dotted lines are glaciogenic deposits. So much of the Peter Fauld's mine, contrary to what the RAF believed, they were mining with something like 30 metres of glacial drift over the top and no rock to speak of. This is the seat of the detonation. These finer hashed lines are the blast walls that confined the explosion and protected the underground store to a large degree. The blast walls forced the locus of the explosion to take off all of the 30 metres of glacial drift and propel it over a kilometre into the air, which also generated a subsidiary air blast which moved laterally across the countryside, demolishing most of the buildings in its path. So what rose up had to come down, and that peppered them, those people that were around, with the bombs, and also all the glacial drift and a lot of the alabaster, which was also brought up and fell back down to earth. So in conclusion, the blast wall did its job, but it concentrated the effects of the detonation and it restricted damage to the installation. But unfortunately, it passed all the damage on to those people that were living on the surface. What we can conclude now is that the design failed because the failure or as a result of the failure to recognise the influence of the thick overburden of weak glaciogenic deposits, and this caused cratering rather than confining the explosion. A rock overburden would have formed what's called a camouflage, which is an underground cavity, and would have reduced the surface impact damage. And most of the casualties as a consequence were the collateral effects at the surface. They shouldn't really have been mining nearby because all the guys who were working there got gassed. Because it was an official secret, there was no memorial erected to those that died until about 2000. Somewhat bitterly, this was the memorial that the Italians erected. So they brought some Italian granite, but we weren't allowed to put our memorial up until 2014, which I was rather pleased to see. And we had quite a ceremony at the time. This is the crater today, extensively wooded. You can still see some of the alabaster blocks just in the bottom, the white bits and pieces. And that brings me to a conclusion. Thank you very much for listening.